All right, let's try not to let the schedule slip too much. So we'll go ahead and get started with our second session today. So we have three short talks by the XENON collaboration. And our first speaker today is Tianyu Zhu. Would you please share your screen when you're ready?
Yes. Set host to disable screen sharing.
Oh, let me add you. One moment. Sorry about that. Oh, actually, Chloe, I think you have to do it.
Chloe, are you back from the break? Just so we know. Can you reclaim host, Scott?
I don't
I
think I can.
I think there's a button called reclaim. Hold on.
Sorry about this, everyone.
Tianyu, just can you try sharing now?
Mm-hmm. Oh.
I am back in case there's anything I can do to help.
Did you make Tianyu and the other speakers for this session co-hosts?
Yeah, of course. Okay, so Tianyu is now a co-host, and I will get everyone else too.
Okay, perfect. Tianyu, now see if you can share your screen.
Sorry. Oh, sorry. So for some reason, I have security issue with the Zoom. Maybe I need to come back later. I don't want to waste your time.
We can change the order if is Shixiao here?
I think their talk's built up. Let me do this.
Okay.
I'm going to load your slides, and then you shout next slide.
It doesn't look like Ashley Lee is in the meeting currently. Correct me if I'm mistaken, please. But everybody else talking for this session should now be a co-host.
Okay, thank you.
Yeah, no problem.
Great. Tianyu, do you want to
Yep.
just shout next slide?
Sorry. Yeah, thanks so much, Chris. So hello, everyone. I'm going to give a brief overview of the signal corrections actually learned by human we applied in XENON 110 dark matter detector. Next slide. So we think those signal corrections are rather essential that we learn from the detector properties that can eventually goes into the reconstruction of position reconstruction and the energy reconstruction. So XENON 110, in brief introduction, is a dual phase time projection chamber, which means it has an S1 and S2 signal. And we also put two array of PNTs on the top and the bottom, the cylindrical PM detector. So for each event, ideally, we will detect 4 sets of signals. So the S2 top and bottom, and the S1 top and bottom. And for the positional case, since those S2s are produced right beneath the top array, and as you can see on as circled by the blue, that we can use those signals to reconstruct the XY position. Z position come naturally from the distance between S1 and S2. And traditionally, we use the rest set 3 sets of data, S1 top and bottom and S2 bottom, to calculate the energy of each event. So, and the following to talk from Andrii and Shixiao will be going into how we use those positions, those pattern to reconstruct the position and energy. So next slide. What I'm going to talk about is some corrections we applied before we do those to facilitate, in a way, facilitate those reconstruction. So one thing we have noticed is that this saturation problem or issue, that for an S2 getting larger and larger, especially for the top PMT arrays, we saw pulses being truncated due to limited dynamic range of ADC. And we also saw it's possible from some S2 has such a large current that our PMT or amplifier goes into this nonlinear regime, that we can no longer trust just the area of the pulse. However, we do devise a method that, as we saw in the previous slides, that even we have very large pulses in certain PMTs for S2, we still have quite a lot of PMTs that response are essentially correct, are not enter into this saturated region. What we do in a rather rudimentary way is that we use the sum waveform of all the non-saturated PMTs and scale those sum waveforms up to match the waveforms that are truncated or we consider non-correct. Next slide. So one effect from this we observed and we think is rather essential is it facilitated the position reconstruction. Imagine when you have PMT giving you a nonlinear result, your position reconstruction algorithm might not know that. And that's what happened in XENON 110. Before using this correction, when we look at rather high energy line at 2.6 MeV, high energy for XENON detector, is that we saw events are reconstructed with an inward bias. They are essentially all grouped together into right underneath a certain PMT. And with this correction and apply our original position reconstruction method, we saw the events are correctly positioned as fitting, shown here, fits our Monte Carlo prediction. Next slide. So moving on from position reconstruction, we also apply several corrections that facilitate the energy reconstruction of our TPC. Something we might commonly know is that the S2 signals do have both S1 and the S2 signal have this position dependent light detection efficiency, especially for S2 as it's when the electron drift up towards the surface, they are being absorbed or captured by some electron impurities. And we do correct the size of S2 based on these steps. However, this electron, this impurity or this fraction of electron being captured is not a constant given time, as those impurity being filtered throughout the whole lifetime of the detector. So we constantly doing those krypton calibrations, those source to calibrate our detector to have this response corrected. Next slide.
Just a couple more minutes, and then we should move to the next speaker, I think.
Thanks. With the same source, krypton 83M, we also observed that it should be uniformly distributed in the TPC. However, we do observe this missing corner at the edge and bottom of a TPC. What happens is that the charge signal from the events drifted inwards because charge up on the wall. And essentially in XENON 110, what we did is to look at the distribution and smooth this distribution out. Essentially using a map to map the observed position into what we presume a uniform distribution. Next slide. Maybe we can skip this and next slide. So given all those techniques, all those corrections we eventually map this color plot in S1 and S2 space for both single scatter and multiple scatter into the energy space. So the energy is actually on this top plot with the red and the blue lines. So originally we can see the S1 and S2 with certain energy lines in this anti-diagonal position. And once we have this mapping within the light yield and the charge yield, basically the angle of this anti-diagonal lines, we map that into a 1D space, which is the reconstruction energy. And the next slide. And that's all I'm going to talk about. Thank you. And here's our lovely collaboration.
Thank you, Tianyu. So I don't know if we want to do, we're still probably waiting on some people to enter questions, but do we want to do questions after each speaker? Is that most logical?
We can just, if people want to type in any right now, otherwise we can do a big one at the end. We'll see if anything comes in.
Okay, sounds good.
While
If there are questions as we move, we'll have them. And if not, we can also have questions referred to the previous XENON speakers if they come up. So
what sort of events produce a saturated S2 signal? You're muted, Tianyu.
Those are the events with about like MeV scale energy gammas. And if they happen on the top, they will definitely saturate the top PMT area.
Yeah. Shixiao, do you want to start sharing?
Okay, is that shared successfully?
Yep.
Okay. So again, I think I can start. Hello, everyone. My name is Xiaoliang. I'm a graduate student at Rice University, also a member of XENON collaboration, and I'm going to talk about graph neural network for position reconstruction. First, I want to talk about the problem we're dealing with. In our TPC, we reconstruct XY position of events with S2s. But S2s come with many noises such as afterpause and filter ionization signals. Also, we lose some information due to dead PMTs and saturations. And as a result, some surface events are reconstructed inside the fiducial volume and become a major background for dark matter search. Also, some of the events are reconstructed outside the detector, which is physically impossible. The way we usually deal with these problems is by making a lot of corrections manually, and Tianyu just showed us in the last talk. So we DIDEX are trying to do that in another way, and we are a collaboration of physicists and machine learning experts. We have Rice University on the physics side, and Rutgers and University of Delaware on the engineering side, and we're trying to handle these problems at a reconstruction phase with some new techniques. And the idea is to embed physical knowledge such as the position of PMTs and the fact that our TPC actually has a wall into the algorithms. The graph neural network is one of the directions we are walking on. So what is it? And that is basically the deep learning on graph structure data. And we have heard about that once an hour earlier. Basically, the data is represented as a node, and the edges represents the connection, the relation between nodes. So in a graph neural network, a neuron is a node, and edges are connections between neurons. So in this way, the information passes between nodes to the edges. Why are we using this? It's because the layout of XENON 1 top array can be better represented by a graph than other structures. Also, as a graph neural network, or just like a CNN, we have many nice features and we want from CNN also present here, such as it's using a shared weights, so that can prevent overfitting naturally to some extent. Also, because it's looking at a small area at a time, so it should be able to ignore some irrelevant signals happen far away from the main S2. And we have built a graph neural network to check this idea. To make things easy, we assume a perfect detector with all PMTs working, and we took each PMT as a node and constructed a graph using Delaunay triangulation. That is basically connect every PMT with other PMTs next to it. And the network was implemented with a library called PyTorch Geometric with PyTorch backend, and the model was trained and evaluated on Gen 4 based optical simulation. So we can see the structure of our models here. We give 3 features in the input layer. There are X, Y position of the PMT and integrated S area. Then we feed that into 2 graph convolutional layer with 16 and 28 features respectively. Then we flatten the output and give that to 2 dense to get the X and Y coordinate of the S2 as the output. So we train that on about 800,000 simulations, and we get a final mean squared loss about 0.1 centimeter squared. Evaluation on 200,000 simulation showed that the resolution of this model on X and Y direction is about 0.3 centimeter, and that is the same level of performance of the multi-layer perception that we used in all the XENON one-time papers. And this indicates our idea, what we are doing here actually makes sense. So next step is we're going to improve that. Very important thing is to figure out what kinds of graph construction make most sense, especially after we remove all the dead PMTs, and we need to add more information into our simulation and add time domains so that some photoionization happen after the S2 can get discriminated automatically and find adequate pooling method on graph. That's an essential part of the neural network. In long term, we want to train the model on data taken by XENON one time, but not simulation. And we'll try to reconstruct position and energy at the same time. To summarize, we have this DIDAX collaboration working on reconstruction problem. And I've talked about graph neural network and showed model we've trained. And we have a lot of exciting works going on.
Great, thank you, Shixiao. So we have a couple of questions here. There's one question: are there distances built into the network or just adjacency?
Oh, the distance are not built into the network in this configuration. They're just adjacency. Oh.
And I'll just ask a follow-up to that.
But they could be.
Right.
It could
so,
be, yeah, in the
so
future.
in a previous talk today, there was an architecture where basically all of the voxels were connected to each other instead of just adjacent things. Have you considered that, or is this just the simplest first case?
So what I'm showing is the simplest first case, and we just have adjacency between PMTs and other PMTs next to it. And of course, we can change the graph construction and add more other information into that, and we expect a better performance with that. But those works are not in a shape that we can present.
Understood. I think we have a hand raised by Hagit. Would you like to say something?
Yes, I think that the fact that you have the X and Y as input, these are positions, so implicitly you do have the distances built into the network. Right? You have the X position and the Y position for every node, then you do have implicit distance there, isn't it?
Yes, but what I mean is they're not embedded into the edges.
But they are embedded into the nodes.
Yes, that
Right. The information is still captured, just not directly through the architecture. Okay. So we have another question. Why is pooling needed?
well, I think that's an essential part of the neural network because, like, if we use pooling in the CNN, we are selecting the most important feature at that area, and we need to do that also to this network. As we can see, we are just adding features like the features is just a channel, work just like a channel in a convolutional neural network. So we are not reducing the dimension at all. And pooling is an essential way to reduce the dimension. And I think that can also help us to get rid of some small signals which are more likely to be noises.
Great. We have another question. What is the advantage of applying a GNN instead of traditional likelihood fitting?
Well, what I was told is the traditional likelihood fitting in XENON 1 term is very slow, and in this way, we're doing that much faster. Also, for likelihood fitting, I don't think like the structure of the layout of the top array is embedded into the algorithm.
Great.
Does that make sense? I guess.
Yeah. We have maybe time for one more question. It's did you look into reconstruction error as a function of position?
Yeah. So on this very simple Gen 4 based optical simulation, the error is let me just show that on this phrase. We have like a fiducial volume is the central volume of the TPC, and the error is pretty small here. And most of the large errors are the events are near the wall of the TPC, and I would say on the optical simulation, the error as a function of position is pretty similar to a normal multi-layer perception.
Great, thank you. Actually, let's just do the very last question. Can you say a bit more about removing nodes to account for dead PMTs? Is this a straightforward process?
I think that's essentially what we are going to, one of the way we're going to try just to remove the nodes. But I think in that way, we also need to figure out a new way to construct the graph. Otherwise, I think I stopped screen sharing, but those empty place which once occupied by a PMT are not connected, and then harm out the performance of the model. So I think it's straightforward, but we need to consider more about that.
Great, thank you for all those answers to those questions. We
Thanks.
can go ahead and move on now. Our next speaker is Andrii Terliuk.
Yes, can you hear me?
Yes, please go ahead.
Okay, great. I think that you can see my slides, hopefully.
Yes.
So I am going to talk about the convolutional neural networks for S2 position reconstruction. And basically, I mean, as an introduction, I think it was already said multiple times, why do we need S2? So reconstruction, so it's basically one of the most important things we might need in the dual phase TPC. And yeah, and I will just jump directly into the problem. So basically, one of the nice features about reconstructing with neural networks is that it's very fast and can be very precise, and it can be used as complementary to other reconstructions. For example, what Shixiao just said, and so on. And essentially, if you look at the PMT arrays which are used in the by dual phase TPCs, they look somehow like that. This is XENON Anton, and it's essentially to the image. So we basically can apply a convolutional neural network and get the position out of that. The problem is that often, and it's the most logical orientation of the PMTs are located in these hexagonal patterns. So basically they form hexagonal bins. And the linear algebra is made for square matrices, so we need a trick to transform that into the arrangements for neural networks. And one of the ways to do that is shown on this slide, on slide number 4. So we're using, so I'm playing with so-called double width transformation, where when you have a hex, for each row, you introduce extra pixels between PMTs, as shown here in the picture, and you sort of shift every row by 1/2 of a pixel. And you introduce those empty pixels, and then you can use absolutely standard, basically very standard convolutional neural networks. An advantage of that you have translational symmetry. So basically the same pattern in one part of the detector and another part of the detector would look, well, the same. Of course, there is a small disadvantage that actually images are slightly larger in memory, but yeah. So yeah, and I tried that, and I'm applying that to XENON Anton, as shown here. So here you can see an example of transformation. So here on the left, you see a top PMT array and a pattern of some S2 and its true position. And then you can see what happens after the transformation. You can see that there are empty bins, yeah, it's basically histogram, so empty bins, so empty entries. And then there is a pattern, and it's kind of localized here. And we tried to train a simple CNN on that. Currently, it's not really optimized. It's basically 3 convolutional layers, 1 max pool layer, and then 1 dense layer and the output layer. So why we are doing that? So for now, it's because we are developing something else in the background, but also we want to use standard layers for now. So we can use it on every machine, and yeah, it's very easy and fast to get into. But of course, the disadvantage of using that there are some extra parameters we are dragging along. So this 65,000 of trainable parameters, in reality, it's a bit less than that. And we trained the network, and you can see the resolution here on the right in the plot. So it's shown as a function of the S2 amplitude. And on the y-axis, you see the 68% resolution, which we can achieve. And different colored lines show what happens if you train on different amplitudes. So if you train here in red, if you just inject 10 electrons, you see like this, and there is this range of amplitudes it trains on it. And blue one, it's 1,000 electrons for S2. It's this range of amplitudes. And you basically see how different networks perform on different amplitudes, but there is no secret here. If you train on higher amplitudes, it performs better on higher amplitudes. If training on lower amplitudes, it performs on better amplitudes. But it shows rather good performance in general, and we can probably optimize training depending on the actual physics study we need. And just a side note, I'm actually using a full simulation here. So when I show PEs, this actually includes all the light propagation and the PMT detection effects. Currently, there is no diffusion, but that's for our benchmark case for now. And another thing we are trying to do is switching off some PMTs in simulation and seeing how the performance degrades. So here on the left-hand side plot, you can see what happens. You see that we switched off in our simulations for PMTs, and then we use the same neural net as we trained without, so it doesn't know that there are missing PMTs, and you can see that it degrades rather badly. So this is events with energy distance, this reconstructed distance more than 20 millimeters. So error is larger than 2 centimeters, and it's nicely clustered around those PMTs. However, if you train and let the network know that there is some missing information, missing bins, it manages to rather effectively counterplay that, and actually, it performs reasonably without much of the degradation of the resolution. And as it's a short summary, I will just go to next steps and summary. So currently, we are working on implementing the proper hex convolution layers instead of using standard TensorFlow layers. And here are examples of, for example, kernel with radius of 3, so central PMT, and then 3 rows of PMTs around, or kernel with radius of 2. So we work on that. It helps to reduce number of training parameters, and also hopefully we can implement more physically driven P6 rotational symmetry for this CNN. And as a summary, we showed that we can actually apply, and this method of double width transformation works rather well. We expect an application to the data soon, because at the end, that's what defines performance. And currently, yeah, we're working on these new hex layers. Okay, that's all from my side. And do you have questions or comments?
Great, thank you. We do have a couple of questions. I'll just go in the order that they're showing up here since we don't have upvotes, but the audience, please vote if you have interest in particular questions. So Igor asks, is it even physical to get 2mm resolution with 3-inch diameter PNPs?
That's what we see, because actually what happens, you basically have a weighted, it's not really a weighted average, but it's not only one PMT which sees the signal, it's like many PMTs around, and slight asymmetry of the image lets network know. So we can, I mean, it seems like we can get to that precision. Of course, in terms of physics, there is another problem of diffusion, and that effect is not included. But without diffusion, I'm pretty sure that we can, because we're using full simulation and it seems to work well.
And this, yeah, everything here is simulation based, right?
Yes, we don't have that data that can be used for that yet.
If I can follow up, because I'm just very curious, I totally accept your answer, but is there any physical limitation, even considering that you can amplitude weight? Did you think about any possible physical, is it 0.2 millimeters? Or can you go to nanometers with enough statistics?
It's a hard question to answer. I don't know the answer. I was trying to think about what is the ultimate precision we can, because it would be a nice benchmark how well we can achieve it. But I don't have a number. I don't know how to estimate it, to be honest.
Yeah, me neither. But I agree, it would be interesting to check. Thanks.
Okay, we have a question. With the double width transformation, you sparse and quantize the data. Naively, this is not ideal, right? What can you comment on that?
So, I mean, yes, this is not ideal. That's why we are working, basically for now, it's me working on that hex transformation where I'm using sparse matrices. So hopefully it will be working a bit better.
Okay.
But currently you're right, there are many of the parameters which are basically trained around and they don't play a huge role.
There's a question, could you combine multiple approaches, CNN, GNN, likelihood fitting, into a single output with a final fully connected neural net layer?
We're sort of thinking about moving in that direction, at least having pre-calculated meta variables, like different kinds of COGs or different kind of, like in high energy physics, like HELAS parameters, something like that. And then using that in a parallel connected network and then combining that as the final layer, but it is very, very preliminary. It's basically idea now, it's not implemented yet.
Great. One last question. Did you have a chance to do back-to-back comparison of performance with standard and hex CNN?
I currently, what I see that this hex CNN, these hex layers, perform rather similarly in terms of precision, in terms of positional construction. However, I see slight degradation of speed, but that's basically because of the sparse to standard tensor transformation, tensor flow. So this is, but in terms of precision, they are working really, really closely to each other.
Great, thank you very much. I think that's all for questions right now. But as a reminder, one of our discussion sections will be on position resolution, specifically in liquid xenon TPC. So there will be time for more follow-up. So why don't we move on to our next speaker. This is Tianyu talking about machine learning and super CDMS.